Good evening and welcome to a new course about the Dirac delta, which is often called the Dirac delta function, even though it is not a function. And at the end of the course, I'll say something about RLC circuits. Now that we have studied linear equations and the Laplace transform, we can finally solve the full equation and say more about the general case for these circuits. So recall from last time, the Dirac delta can be defined as the weak limit of a sequence of functions whose graph is a tall and narrow peak such that the area under the graph of the function is 1. So it's these functions, fa of t is 1 over 2a when t is between minus a and 0 when absolute value of t is bigger than a. So here is a graphical representation. These are the functions fa that have a rectangular graph. So in other words, the area under the graph is a rectangle. And as the graph gets taller and narrower, so as a goes to 0, then the weak limit of this is the Dirac delta function. Well, the Dirac delta is the weak limit of these functions, but it is actually not a function. It is a measure and a distribution, both of which are notions that can generalize the notion of a function. We can recall the Dirac delta function, or measure, is the one that represents a point mass at 0. But if we want to represent a point mass at another point, then we should use a translate of the Dirac delta. In general, the family of these translates are called delta A of t, which is delta of t minus a, and they can be used to represent a point mass at any point a. So in particular, delta 0 is the original Dirac delta. So they correspond to a point with infinite density and, of course, 0 width. The following property of the Dirac delta function can be taken as a definition, namely the integral over any interval I of a continuous function f of x times the Dirac delta at a point x0 is equal to f of x0 if x0 belongs to the interval I, and 0 if x0 does not belong to the interval I. So this is the property of the Dirac delta function that we'll use in computations. Okay, so here is a first such computation. Let's compute the convolution of a function, of any function, with the Dirac delta sub a for a greater than or equal to 0. By definition, this is equal to integral from 0 to t of f of t minus tau delta a of tau d tau. So there are two possibilities. Either A is in the interval 0t, meaning that 0 less than or equal to A is less than or equal to t, or A is not in the interval 0t, meaning A is bigger than t. If A is not in the interval 0t, then by the formula from the previous page, the integral is 0. If A is in the interval 0t, then again by the formula on the previous page, the integral is equal to f of t minus tau evaluated at the point tau equal a, which gives f of t minus a. So taking the convolution of any function f with delta sub a moves the graph of f on 0 infinity by a to the right, and the remaining gap between 0 and a is filled with the value 0. So the reason why the Dirac delta works in this manner is that the Dirac delta, first of all, is 0 everywhere outside the point x equal x0. So when you integrate f times the Dirac delta, nothing contributes except the point x equal to x0. So in particular, if x0 is not in the interval I, then there is no contribution at all to this integral. If x0 is in the interval I, then all that measures is the value of f at the point x0. And then this integral could be replaced by integral of f of x0 times delta x0 of x. And since the Dirac delta has total mass 1, then its integral is 1, and we are just left with f of x0. Okay, so here is a practical computation that we'll use in the course. What is the inverse Laplace transform of e to the minus 2s over s minus 3? Well, we can write e to the minus 2s over s minus 3 as e to the minus 2s times 1 over s minus 3. And then the inverse Laplace transform of the product is the convolution of the inverse Laplace transforms. So this is the inverse Laplace transform of e to the minus 2s, convolution with the inverse Laplace transform of 1 over s minus 3. And the inverse Laplace transform of 1 over s minus 3 is e to the 3t. And in the previous course, we also computed the inverse Laplace transform of e to the minus 2s, and we got delta 2 of t. So this is because the Laplace transform of delta 2 of t is e to the minus 2s. And now, using this previous result for convolution with Dirac delta, the convolution of delta 2 of t and e to the 3t is, well, so it is the function e to the 3t when the interval 0 infinity shifted to the right by 2. And so we have 0 when t is between 0 and 2. So that's the gap left behind by shifting the function to the right by 2, and it is e to the power 3 times t minus 2 when t is greater than or equal to 2. Okay, so now let's apply this to solving an ordinary differential equation involving Dirac deltas. Let's consider the initial value problem. Y double prime minus y is equal to 5 delta 1 of t plus 3 delta 2 of t with the initial conditions y of 0 is equal to 1 and y prime of 0 is equal to 2. Let's apply the Laplace transform to both sides, which we know how to do now because we computed the Laplace transforms of the Dirac deltas. So letting Laplace transform of lowercase y be uppercase y, we get s squared uppercase y minus sy of 0 minus y prime of 0. So this is the Laplace transform of y double prime. And then minus capital Y, which is the Laplace transform of lowercase y, is equal to 5 times the Laplace transform of delta 1, which is e to the minus s, plus 3 times the Laplace transform of delta 2, which is e to the minus 2s. So in general, the Laplace transform of the Dirac delta at A is e to the minus as if A is greater than or equal to 0. Okay, so grouping the terms containing capital Y together and putting everything else on the other side, we get s squared minus 1 times capital Y is equal to, so sy of 0 was s, because y of 0 is 1, and then plus y prime of 0, which is 2, plus 5 e to the minus s plus 3 e to the minus 2s. So capital Y is equal to s plus 2 plus 5 e to the minus s plus 3 e to the minus 2s over s squared minus 1. Okay, so capital Y is equal to s plus 2 plus 5 e to the minus s plus 3 e to the minus 2s over s squared minus 1. And then in order to compute the inverse Laplace transform of this, we should decompose it into some simpler parts whose inverse Laplace transforms we know. So first of all, for s plus 2 over s squared minus 1, we can just use partial fraction decomposition, and computing the coefficients, we get that it's equal to 3/2 over s minus 1 minus 1/2 over s plus 1. And we want to also simplify the rest of the expression. So 5e to the minus s over s squared minus 1 and 3e to the minus 2s over s squared minus 1. So let's decompose 1 over s squared minus 1 into partial fractions. And we get that it's equal to 1/2 times s minus 1 minus 1/2 s plus 1. Okay, so then we apply this to all the components of capital Y, and we got that capital Y is 3/2 times 1 over s minus 1 minus 1/2 times 1 over s plus 1. So this is from the decomposition of s plus 2 over s squared minus 1. And then from 5e to the minus s over s squared minus 1, we got 5/2 e to the minus s over s minus 1 minus 5/2 e to the minus s over s plus 1. So we replaced 1 over s squared minus 1 by 1/2 times 1 over s minus 1 minus 1 over s plus 1. And then from 3e to the minus 2s over s squared minus 1, we got 3/2 e to the minus 2s over s minus 1 minus 3/2 e to the minus 2s over s plus 1. Right. So the solution, lowercase y, is the inverse Laplace transform of this expression. And the good thing is that we know how to compute the inverse Laplace transform of each term. All right, so the solution lowercase y of t is the inverse Laplace transform of this sum. And as I said, we know how to compute the inverse Laplace transform of each term in the sum. So as we have already done in previous courses, the inverse Laplace transform of 3/2 over s minus 1 is 3/2 e to the t, and the inverse Laplace transform of 1/2 over s plus 1 is 1/2 e to the minus t. So this is just the Laplace transform, or the inverse Laplace transform of 1 over s minus a, which is an exponential. So this is the Laplace transform of exponentials. What about the other terms? So here again, we have to use the Dirac delta function. Well, let's look at one of them. Let's say the Laplace transform, the inverse Laplace transform of e to the minus s over s minus 1 is, well, e to the minus s over s minus 1 is the product of e to the minus s and 1 over s minus 1. So then, by the properties of the inverse Laplace transform, we get that this is equal to the inverse Laplace transform of e to the minus s convolution with the inverse Laplace transform of 1 over s minus 1. The inverse Laplace transform of e to the minus s is the Dirac delta at 1. So the Dirac delta supported at 1. And the inverse Laplace transform of 1 over s minus 1 is e to the t. Right, so their convolution is e to the t translated to the right by 1. So we take the graph of the function e to the t on the interval 0 infinity and move it to the right, shift it to the right by 1. In the gap, so between 0 and 1, we fill by 0. And then when we move e to the t to the right by 1, we get e to the t minus 1. All right. What about, for example, the inverse Laplace transform of e to the minus 2s over s plus 1? So this is the inverse Laplace transform of e to the minus 2s convolution with the inverse Laplace transform of 1 over s plus 1. The inverse Laplace transform of e to the minus 2s is the Dirac delta at 2, and the inverse Laplace transform of 1 over s plus 1 is e to the minus t. So the convolution of delta 2, delta sub 2, and e to the minus t is e to the minus t translated to the right by 2. So we take the function e to the minus t on the interval 0 infinity and move it to the right by 2. And in the gap, so in the remaining space between 0 and 2, we fill it by 0. So then this result is 0 when t is between 0 and 2, and e to the minus t minus 2 when t is between 2 and infinity. So in the same manner, we can compute the inverse Laplace transforms of the other two fractions, e to the minus s over s plus 1 and e to the minus 2s over s minus 1. So in both cases, we get an exponential function on the interval 0 infinity moved to the right by 1 or by 2, depending on whether we take the convolution with the Dirac delta at 1 or the Dirac delta at 2. So combining all of these terms and taking into account the coefficients of 5 halves or minus 5 halves, we get that y of t is equal to, so first we have the terms that come from the fractions 3 halves over s minus 1 and minus 1 half over s plus 1. So that gives 3 halves e to the t minus 1 half e to the minus t. And then we have the terms coming from these more complicated fractions that involve the Dirac delta functions. So we get 5 halves times 0 when t is between 0 and 1, and e to the t minus 1 minus e to the minus t minus 1. So I combined two of the terms on the previous page. When t is between 1 and infinity, and then plus 3 halves times 0 when t is between 0 and 2, and e to the t minus 2 minus e to the minus t minus 2 when t is between 2 and infinity. So this comes from these two fractions. So again, I combined two terms. Okay, so now if we want to write the function y in a more intelligible way, we should look at what it is on the intervals 0, 1, 1, 2, and 2 infinity. So this function will be given by three different expressions. One on the interval 0, 1. Another expression between 1 and 2, and another expression on the interval between 2 and infinity. So this is because the inverse Laplace transforms of these more complicated terms change at 1 and at 2. So these are the two transition points where the function changes. So on the interval 0, 1, the function is equal to 3/2 e to the t minus 1/2 e to the minus t. So as you can see, on the interval 0, 1, we only have the contribution from the first term, 3/2 e to the t minus 1/2 e to the minus t. And the other two terms here are 0. So this term is 0 on the interval 0, 1. This term is also 0 on the interval 0, 1. Then on the interval 1, 2, function is given by the sum of two expressions. So it's 3/2 e to the t minus 1/2 e to the minus t plus 5/2 times e to the t minus 1 minus e to the 1 minus t. So as you can see on the interval 1, 2, we get two contributions. So we get 3/2 e to the t minus 1/2 e to the minus t, and then we get plus 5/2 times e to the t minus 1 minus e to the minus t minus 1. And the third expression still doesn't contribute because on the interval 1, 2, the third expression is 0. And finally, on the interval to infinity, all three expressions contribute. So we get 3/2 e to the t minus 1/2 e to the minus t plus 5/2 times t to the minus 1 minus e to the 1 minus t plus 3/2 times e to the t minus 2 minus e to the 2 minus t. So as you can see, all three expressions contribute. This expression doesn't have any different cases. It always is equal to 3/2 e to the t minus 1/2 e to the minus t. The second expression on the interval 2 infinity, which is included in the interval 1 infinity, we get 5/2 times e to the t minus 1 minus e to the minus t minus 1. And the third expression on the interval to infinity is equal to 3/2 times e to the t minus 2 minus e to the minus t minus 2. And finally, as an observation, because we have such terms as these Dirac delta functions on the right-hand side, we can check that the solution y of t is continuous and its derivative is continuous, but its second derivative is not continuous. So this is not a classical solution, meaning that y double prime is not well defined at every point. Okay, so let's consider another example to see how the Dirac delta can appear in an application. So the Dirac delta corresponds either to point masses or to instantaneous events, that is, events that happen suddenly, without duration. So they happen in just one moment. Okay, so let's try to solve this problem. A bank account starts with $1,000 at the beginning of the year and earns 5% interest with continuous compounding. After half a year, a deposit of $500 is made into the account. After a year, a withdrawal of $300 is made from the account. How much money will there be in the account after 2 years? So instantaneous events like these sudden deposits and withdrawals can be modeled by using Dirac deltas. So if the deposits or the withdrawal were done over time, then we would not use a Dirac delta to model them. If they are done at once, so it just takes one moment, then they are modeled using Dirac deltas. Okay, so let the amount of money in the account be A of t. Then A of t is a solution of the initial value problem, A prime minus 0.05a is equal to 500 times the Dirac delta at 0.5 minus 300 times the Dirac delta at 1. With the initial condition, A of 0 is equal to 1000. Right, so what does each number represent? So A of 0 is equal to 1000 is the initial amount of money in the account. A prime is equal to 0.05a is the equation that describes the exponential growth of the amount of money in the account under continuous compounding with 5% interest, if there are no deposits or withdrawals. So then the equation would just be A prime is equal to 0.05a. And the other terms represent the deposits and the withdrawals. So if they are instantaneous deposits or withdrawals, then they can be represented by Dirac deltas. So 500 times delta 0.5 is a source term that represents a deposit of $500 at a time of 0.5. So this means after half a year. And minus 300, the Dirac delta at 1, represents a withdrawal of size 300 at time 1. So these source terms show what other interventions there are in the system other than the continuous compounding of the interest. So if the equation only had the initial amount of money and continuous interest compounding, it would be A prime is equal to 0.05a. And since we have deposits and withdrawals, we have extra source terms, which in this case are represented by Dirac delta functions because they happen instantaneously. So let's solve this initial value problem by the Laplace transform, even though this may not be the easiest way of solving it. Let the Laplace transform of capital A of the amount of money be capital Y. Then the Laplace transform of A prime is S times capital Y minus A of 0. Then what do we get when we apply the Laplace transform to the whole equation? Laplace transform of A prime, which is on the left-hand side again, is S times capital Y minus A of 0, which is 1000. And then so the Laplace transform of 0.05a is 0.05y. And the Laplace transforms of the Dirac delta terms are 500 e to the minus 0.5s and minus 300 e to the minus s. Okay, so grouping all the terms with capital Y together, we get S minus 0.05 times capital Y is equal to 1000 plus 500 e to the minus 0.5 S minus 300 e to the minus S. Then capital Y is equal to 1000 plus 500 e to the minus 0.5 S minus 300 e to the minus S over S minus 0.05. And if we just split this fraction into 1000 over S minus 0.05 plus 500 e to the minus 0.5 S over S minus 0.05 minus 300 e to the minus S over S minus 0.05, then we know how to compute the inverse Laplace transform of each term, so we can find the solution. So the inverse Laplace transform of 1000 over S minus 0.05 is 1000 times e to the 0.05t. So this is just an exponential. Laplace transform, the inverse Laplace transform of 500 e to the minus 0.5 S over S minus 0.05 is an exponential shifted to the right by 0.5. So this e to the minus 0.5 S factor in the numerator has the effect of shifting the answer, of translating the answer by 0.5. So you get 0 when t is less than 0.5, and 500 times e to the 0.05 times t minus 0.5 when t is greater than or equal to 0.5. And the inverse Laplace transform of minus 300 e to the minus S over S minus 0.05 is again an exponential shifted to the right by 1. And the solution is the sum of these three terms. And we notice that the solution will be given by three different expressions with transitions occurring at 0.5 and at 1. So there will be three different answers: one answer for the interval between 0 and 0.5, one answer for the interval between 0.5 and 1, and one answer for the interval 1 infinity. All right, so what is the answer? We get 1000 times e to the 0.005 t on the interval between 0 and 0.5. So this is because on this interval, only the first term contributes. And then 1000 e to the 0.05 t plus 500 e to the 0.05 times t minus 0.5 on the next interval, because there we have contributions from two terms. So notice that between 0.5 and 1, we have contributions from 1000 e to the 0.05 t and from 500 e to the 0.05 times t to the minus 0.5. So this is because this is the value of the second term on the interval where t is greater than or equal to 0.5. And the third term does not contribute because we're looking at the interval between 0.5 and 1, and the third term is 0 on the interval between 0.5 and 1. Finally, on the interval between 1 and infinity, I get 1000 e to the 0.05 t plus 500 e to the 0.05 times t minus 0.5 minus 300 times e to the 0.05 times t minus 1. So in this interval, we have contributions from all three terms. So indeed, if you look at these formulas, the first term always contributes because it's always given by 1000 times e to the 0.05 t. The second term contributes as well because you are looking at the case when t is greater than or equal to 1. So this is included in the case when t is greater than or equal to 0.5. And the third case, the third term contributes as well because again we are looking at the case when t is greater than or equal to 1. Our original question was, what is the amount of money in the account after 2 years? So this means we are trying to compute A of 2. So if we look at the formula, then 2 is in the interval 1 infinity. So we should use the third formula. And if we plug 2 into the third formula, then after doing the computation, we get $1,328.73. So this is the correct answer for the amount of money after 2 years. All right, so now let's have a look at RLC circuits and solve the equation by means of the Laplace transform. So an RLC serial circuit can be described by the equation L times the second derivative of Q plus R times Q prime plus 1 over C times Q is equal to E of t. Here E of t is the voltage of the external power source, L is the inductance of the inductor, R is the resistance of the resistor, C is the capacitance of the capacitor, and Q is the charge stored on the capacitor. We are usually more interested in finding out the electric current, the intensity of the current going through the circuit, and that is related by the charge to the charge by the relation I is equal to dq over dt. So the intensity of the current is equal to the derivative of the charge. So now let's solve this equation by means of the Laplace transform. Let's consider the initial value problem. L q double prime plus R q prime plus 1 over C q is equal to E of t, where we have the initial conditions. Q at time 0 is equal to Q0, and Q prime at time 0 is equal to I0. So the derivative of the charge is the intensity, and I0 represents the intensity at time 0. Let the Laplace transform of the charge Q be capital Q. Then applying the Laplace transform to the whole equation, we obtain L, which is the inductance, times S squared Q minus SQ0 minus I0 plus R times SQ minus Q0 plus 1 over CQ is equal to the Laplace transform of E. Then grouping all the terms with Q together, we get ls squared plus rs plus 1 over c cubed is equal to sum of all the other terms on the other side. Okay, then the Laplace transform of the charge capital Q is equal to the quotient LQ0S plus LI0 plus RQ0 plus the Laplace transform of E over LS squared plus RS plus 1 over C. And we can split this fraction into terms whose inverse Laplace transform we know how to compute. So we get everything in terms of the fundamental solution. Let the fundamental solution of the equation be the inverse Laplace transform of 1 over the auxiliary polynomial. So it's the inverse Laplace transform of 1 over ls squared plus rs plus 1 over c. Then the inverse Laplace transform of the first term here, LQ0S over ls squared plus rs plus 1 over c, is LQ0 times g prime of t. So in general, this should be g prime of t plus g of 0, but g of 0 is 0. And then it's plus the inverse Laplace transform of Li0 plus Rq0 over L squared plus Rs plus 1 over C. So this is just Li0 plus Rq0 times G itself. And then the last term, when we apply the inverse Laplace transform, we get the inverse Laplace transform of the fraction convolution with the inverse Laplace transform of the Laplace transform of E. So we get the fundamental solution G convolution with the inverse Laplace transform of the Laplace transform of E, which is E. Okay. So the behavior of the circuit depends on the fundamental solution. We see that we can express every solution in terms of the fundamental solution. We could also compute the intensity of the current by taking the derivative of Q. So it's all in terms of the fundamental solution. And when computing the fundamental solution, there are 3 cases according to the roots of the auxiliary polynomial. So when computing the fundamental solution, we take the inverse Laplace transform of 1 over the auxiliary polynomial, and then we could decompose the auxiliary polynomial into factors, and then we can decompose the fraction into partial fractions, and then we get the following 3 cases. If r squared is bigger than 4l over c, then the auxiliary polynomial has real roots. So the discriminant of the quadratic equation, L squared plus Rs plus 1 over c is equal to 0, is r squared minus 4L over c. So if the discriminant is positive, then we have distinct real roots. Then the fundamental solution is a linear combination of decaying exponentials. And in this case, the fundamental solution does not oscillate, and the circuit is called overdamped. So in this case, the fundamental solution just has exponential decay. If R squared is equal to 4L over C, then the discriminant of the quadratic equation is 0, and the auxiliary polynomial has a real double root, which is negative. So these roots are negative because R, L, and C are positive numbers, and then if you plug them into the quadratic formula, you'll get a negative solution. Then the fundamental solution of the ordinary differential equation is a decaying exponential times a linear factor because of the double root. So it's t over L times e to the minus r over 12 times t. So I computed it. And this is a borderline case between the overdamped and underdamped cases. And in this case, the circuit is called critically damped. And finally, if R squared is less than 4L over C, then the discriminant of the quadratic equation is negative. So I am talking about the quadratic equation. Ls squared plus Rs plus 1 over C is 0. And the discriminant of this equation is R squared minus 4L over C. And a quadratic equation with a negative discriminant has complex roots, complex solutions. So the auxiliary polynomial will have complex roots with negative real part minus r over 2l. So the fundamental solution is a decaying exponential times a sine function. Well, it's this rather complicated expression. This is what you get by solving the quadratic equation and by applying the inverse Laplace transform to 1 over the auxiliary polynomial. So we get this expression for the fundamental solution. So the fundamental solution is a decaying exponential times a sine, and it oscillates because of the sine. And in these cases, when in this case, when you have an oscillation in the fundamental solution, the circuit is called underdamped, and then the solutions, all the solutions to the equation will have oscillations. Well, thank you for your attention, and see you next time.